This bead is not resting on air, and gravity has not switched off. It is being held by sound, ultrasound arranged so precisely that it creates an invisible trap. Start with 2 facing rows of ultrasonic transducers. Drive them at the same frequency, with controlled phase. Waves traveling in opposite directions overlap, producing a standing wave, a fixed stack of pressure nodes, where pressure oscillation is small, separated by antinodes, where it is large. At 40 kHz in room temperature air, sound has a wavelength of about 8.6 millimeters. Adjacent pressure nodes are half a wavelength apart, about 4.3 millimeters. Frequency, therefore, sets the basic spacing of the trap. But a node alone does not levitate anything. The bead scatters the sound around it. Because the field is stronger on some sides than others, that scattering transfers momentum unevenly. Averaged over thousands of cycles, the alternating pressure produces a steady acoustic radiation force. For a small, dense bead in a conventional standing wave, that force points toward a minimum in an acoustic potential near a pressure node. Gravity breaks the symmetry. The bead settles slightly below the ideal node, at the position where the upward acoustic force exactly matches its weight. Levitation also requires stability. Nudge the bead sideways or vertically, and the force must point back toward equilibrium. In energy language, the bead must sit in a bowl, not on a flat shelf or a saddle. The curvature of that bowl is the trap stiffness. Steeper curvature means faster, stronger return after a disturbance. There is no universal maximum mass. The available force depends on acoustic pressure and field geometry, while the required force depends on the object's density and volume. Its size relative to the wavelength changes how it scatters sound. Below roughly half a wavelength is a common conventional regime, but finite-size experiments show weak traps, force reversals, and even off-axis trapping at other sizes. Shape, compressibility, airflow, and alignment matter too. For droplets, excessive acoustic stress can flatten the liquid until surface tension loses and the drop breaks apart. A phased array makes the trap programmable. Change the delay sent to each transducer, and the pressure field reshapes. The potential minimum moves, so the trapped bead or droplet follows without being touched. That makes acoustic levitation useful for containerless work, moving tiny samples, mixing or drying droplets, and studying materials without a vessel contaminating them. Researchers have even collected room temperature X-ray diffraction from protein crystals inside a levitated droplet. Sound is not replacing cranes. It is becoming a precise, contact-free laboratory tool, an invisible landscape that can hold matter in place.